just 5 and 6 on this,
Yes, yes. But I want to cover this because I want to cover the material. It's something that's important to cover. Actually, I think it's sad that we only have one power electronics course, but we should have more. But the syllabus is a bit weird. Anyway, so we did some review, but now we're going to go back to chapter 8. So we talked last time about about the inverter topologies, and we introduced the 4-switch, the full bridge 4-switch inverter last time, and we saw that with this topology, I can have a load here. Let's assume it's a resistive load in this case. For a resistive load, if I turn on switch 1 and 2, I'm placing VDC across. This is my V output polarity. So my V output polarity is always fixed. So if I'm turning on 1 and 2, V output is equal to VDC. Right? If I'm turning on 3 and 4, V output is equal to minus VDC. I flipped it. Right? So this is one way to operate these converters. Right? So you just turn 1 and 2 on, and then turn 3 and 4 on. 1 and 2 on, turn 3 and 4 on. And that's what you're building. You're building that after the 12-volt battery charger. Right? You're building a high-frequency AC converter. That's what you're doing, right? This is AC. This is not DC. Right? Why are you doing that? You're doing that because you want to boost the voltage. You want to use a transformer because you want to boost the voltage from 12 volts to 180 volts. And you cannot use a regular boost converter because we saw the limit on boosting ratio is what? 4 times, for example. So from 12, you cannot boost to 180 volts. No way. So what's the solution? The solution is always a transformer. AC, but transformers do not allow you to translate DC voltages. They only allow you to translate AC voltages. Right? The other solution is you can use 2 boost converters in series. Right? If you boost 2 boost converters in series, so 12, you can multiply this by, let's say, 4. What do we get? 48. Multiplied by 4. No, it's closer to 200, right? It's 200 minus 8, right? It's 192, right? 192 volts, right? So you can get your 180 volts. Sure, great. But then you have an efficiency here and an efficiency hit here. What's the total efficiency now for your DC stage, for your boosting stage? This is, let's say, 90%, and this is 90%. Your efficiency would be 0.9 times 0.9, 0.81. So 81% efficiency for the boosting stage. So this is one way to do it, right? Another way to do it is what you're doing in the project. What you're doing in the project, you have a full bridge inverter that you are creating a high frequency AC waveform from. This high frequency AC waveform, is it a nice, beautiful sine wave? No. And I don't care for it to be, because I'm going to rectify it afterwards, right? In your case, in the full bridge DC to DC converter, when you make a full bridge DC to DC converter that has a front end, basically, which is a high frequency DC to AC inverter, you don't care about the frequency content. But if you do the Fourier series for this, what will you find? You will find a lot of harmonic content because it's a square wave. A square wave will have, again, if you go back to a Fourier series, here, this is the Fourier series for the square wave. V of t is equal to 4 V maximum over pi. All of these harmonics, first, third, fifth, seventh, it will contain all of these harmonics. Do I care? In your case of building a DC to DC converter, which you're going to take this waveform and rectify after that, you don't really care. You're not taking this into a load and looking at the power factor or the power transfer or whatever, because you're going to convert this to DC. When you convert this to DC, it's going to look like a nice DC waveform at the end, right? So you're going to rectify this. It's going to look like a DC waveform at the end, but you get the benefit of being able to go through a transformer by doing this, because you have an AC waveform. You can push that to a transformer. If you put DC across the transformer, the winding will not generate back EMF to oppose the voltage that's being placed on it. If there's no voltage to oppose the back EMF, if there's no back EMF voltage generated to oppose the voltage that you're placing across the winding, you place a voltage across a winding here. If this winding is not going to generate an opposing back EMF, meaning will look like this, having a voltage source in series, that's the equivalent circuit of a back EMF voltage developed across the winding. If the winding is not going to do this, then what's going to happen? Then you're placing a voltage source across a piece of wire, basically. So the resistance of the wire will limit the current. That's it. So you're going to be pushing a huge amount of current through. Pushing a huge amount of current through, you saturate the transformer. It's useless. You're not building a transformer anymore. You're building a heater. Right? So only when that the winding is able to generate the back EMF, and when is it able to do that? When you push an AC waveform through it. E equals, the back EMF is equal to N d phi by dt. The back EMF voltage developed across any coil is equal to number of turns multiplied by d phi by dt. The time varying value of flux. Right? So it has to be an AC component, time varying component, to be able to push it through a transformer. Right? So you do this in your circuit. Right? After that, you push it through a transformer and rectify it. The classical rectifier that we studied, the diode rectifier, the full bridge diode rectifier that we studied at the beginning. Right? No problem. This is great. And the equivalent circuit to what you guys are doing is the same as what I've been talking about. Right? This is, at the end of the day, your transformer. Right? It has, what's the model of a transformer? What does the model of a transformer look like? It has a leakage inductance and the leakage and the resistance of the winding, then ideal turns ratio, and then the leakages on the secondary side. And then if you want to consider the magnetizing branch, you can consider that as well. Right? From 338, this is the equivalent circuit of the transformer. So there is an inductance in series as well. So same thing, I have my two switches, have a voltage across them that is fixed. And my output is going through an inductor, right? Nothing changes. All the power electronics topologies are the same. Always the two switches that are operating complementary have a fixed voltage across them. And between them, then there's an inductive current at some sort. It can be a transformer, it can be a big inductor, it can be a small inductor. It depends on your circuit's operation. Right. So you have this this inverter now that is creating this V output that is either minus V input or V input. Right. If you are operating it in a complementary 1, 2, 3, 4, 1, 2 together, 3 and 4 together. Right. And we operate with a duty cycle, a fixed duty cycle, right? If you go ahead and have a fixed duty cycle, but here we're operating. What's the switching frequency that we're operating at? What's the relationship between the output voltage frequency and the switching frequency? This is the frequency of the output. Okay. This is my output waveform, right? It's either V in or minus V in. When 1 and 2 are on, it's V in. When 3 and 4 are on, it's minus V in, right? So this is my period. So what's my switching frequency for operating an inverter in this fashion? What's my switching frequency? Equal to the fundamental, it's equal to the output frequency, right? This is my output waveform. I'm operating switch 1 and 2 here. Then I'm operating switch 1 and 2 here. Then I'm operating switch 1 and 2 here, right? So what's the switching frequency of switch 1 and 2? It's the same as the output frequency, right? It's happening one time every switching period, one time every switching period, right? So it's the same as the output frequency. You agree or not? Guys, come on. Huh? Why not half? No. I mean, remember this is a waveform. It's happening. I have a pulse here. What is the frequency of this waveform? You look at the period, and this is the period. So Fs is equal to 1 over the period. Right? It doesn't matter if this is this wide or is this wide. Right? Does it matter? It's turning on and off during a period. That's the switching period. It's turning on and off one time during this switching period. So what is the switching frequency? It's 1 over the switching period. Right or wrong? No, this is a question that I need an answer for.
Yeah.
Yes? You're not convinced? Yeah.
I don't get how it's the whole period. Like, switching what is the switching frequency in this diagram?
Switching frequency is 1 over the switching period. So think of, okay, you take 4 classes. Does it matter? You take 4 classes a day. That's your frequency of classes. Does it matter how long the class is? Right? So this is happening. You're turning on the device and turning it off once every period. This is my switching period. Right? The turn on duration. You're confusing duty cycle now with the period. Right? Your duty cycle is the time on over the time on plus time off, or this is now the full period. You're confusing both now together. So I'm not asking for the duty ratio. I'm asking for a period, right? Or the inverse of that is the switching frequency. So how fast am I switching devices 1 and 2? I'm switching them one time during this period. So their switching frequency is 1 over this period, right? So this is the frequency of the output. So if I'm supplying a 50 hertz or a 60 hertz system with this inverter, I can, right? Would it be a problem if I plug this computer into this outlet that is being supplied by an inverter that's feeding a waveform like this? Maybe. It depends on the specs of the input specs of this. If the input of this PC is nothing but a full bridge rectifier, no, it doesn't matter. If the input is a full bridge rectifier, if it's taking this AC voltage and just rectifying it, it does not really matter at all. It does not really matter at all. If it's a different thing, if it's a circuit that's intelligent enough to detect, okay, I have too much harmonic content, so I'm gonna be just heating up my board without transferring real amount of power to the system, right? Lots of voltage harmonics, for example, or if this is a current waveform, lots of current harmonics with no power transfer. Then it's a different problem. Some equipment will tell you, we allow for voltage distortion of a certain amount. You exceed the voltage distortion, I will shut down. It's like the thermal shutdown we talked about the other day, right? So, but you can plug this, you can take this inverter and supply an AC load, and no problem, it will work. And the benefit here is I'm switching at a very low frequency, so my switching losses are very low, right? My switching losses, turn on and turn off switching losses are very low, and I'm supplying an AC waveform. It's nice, it's great, but I have a lot of harmonic content, right? The alternative to this is to figure out a way to improve the harmonic. I mean, if you want to create a nice sine wave, you have to figure out a way to create the sine wave, and it's not going to be by switching at fundamental frequency anymore. You have to switch faster to be able to chop up this waveform in a way that you would make it resemble as a waveform that has less content, less harmonic content. So initially, now we started with this simple 4-switch inverter, and we're operating the switches at fundamental frequency. Are we getting, and this is my 50 hertz, this is my 20 milliseconds. If this is a 50 hertz waveform, this is V input, and this is minus V input. Am I going to be able to run my load? Yes, I can. If I connect a heater, is it going to bother the heater? No. The heater will not be bothered at all. If this is my voltage waveform, I have a resistor. I have the current waveform will look exactly the same, and which means I have what? I have voltage harmonics and a corresponding current harmonic. Voltage harmonic corresponding. That means I will be able to transfer full power. I will not be losing power. Remember, when we were talking about harmonic losses, it was because I have a sinusoidal voltage and distorted current. In that case, I have pure sinusoidal voltage at the fundamental frequency and then currents at the fundamental and many others. That many other stuff will not count because the power is equal to V times I at a certain frequency times the cosine angle between them. If I don't have V's at the rest of the I's frequencies, then it's useless. Then all of these other currents are not helping me deliver real power to the system. But here, it's a square wave voltage. If I have a resistor, square wave current, no problem. Life is great, right? But if I have an RL load, the current will not look exactly like the voltage. So I will have there will be some content in the current waveform that is not in the voltage waveform. So I will have some losses there. But assuming it's a resistive load, then this is perfectly fine. The problem is it has a lot of harmonic content. This is something that exists. And if I have an RL load having a lot of harmonic content, means that I have losses, I have current harmonic components that are not contributing to real power transfer, right? So for a resistive load, no problem, it doesn't matter, this is fine. Put a heater, yeah, it will operate as good as anything else. Put an RL load, any other real type load, then you will have a current waveform that will, how will the current waveform look here? RL load. How will an RL load current look in this case? I'm putting this voltage across an RL load. What will the current look like? Again, assume it's an inductive load, okay? Assume it's an inductive load. If it's an inductive load, what will the current look like? A ramp. Where is the maximum value for the ramp? Here. Where is the minimum value for the ramp? Here or also here because I'm periodic, right? So it's a ramp if it's a pure inductive load. How about if it's not a pure inductive load? It's an exponential. So the exponential, it will look like this. It will look like this, right? The harmonic content in this blue waveform is not equal to the they're not equal. I mean, this is a square wave. This is the Fourier series for the square wave. We just saw it, right? We just saw that it's V maximum over pi, and then all the triplet harmonics, first, third, fifth. I mean, so not triplet, first, third, fifth, seventh, etc. So that's the Fourier series for the square wave. Is that the same as the Fourier series for this waveform? No. They will have some harmonics that are in phase. So they will have maybe the fundamental. They may have a third. They may have a fifth. But definitely, this square wave has transitions, significant transitions here. That means that there's a lot more harmonic content in these transitions, fast transitions, than this slow transition. There's a difference. I don't have the Fourier series for this blue waveform. But since the waveforms are not identical, then there's a difference between the harmonic content. That's the basics of by looking at the waveform. If that's the case, that means I have some voltage harmonics that will not find a corresponding current harmonic at the same frequency, and hence will not be able to transfer real power. Is that good or bad? Bad, because I want to deliver AC power to my load. But I have current flowing that is not contributing to P equals V times I cosine phi, which is, these have to be Vx, Ix, same frequencies. If there are currents that are not at the same frequency, then it's useless. I'm not contributing to real power, right? So what do we want to do? We would like to be able to improve the load will not change. So the current is sort of dictated upon us, right? The current is going to be dictated by the load, right? You put a voltage, you create. So ideally, I would like to go and be able to create a nice, beautiful sine wave. That's ideal, right? But before doing that, people developed this in stages, right? So first we had this 4-switch inverter operating at the fundamental frequency of the output. Then, what's another capability I can do with, so this I'm operating either 1, 2, or 3 and 4 together. right? Either 1, 2 or 3, 4. 1, 2 or 3, 4. So it's either Vn or minus Vn. Vn or minus Vn. What's some other option we talked about last time for operating this inverter? I can get Vn minus Vn. And what else can I get out of this inverter at the output here? 0. If I turn on 1 and 4 or I turn on 2 and 3, I can get 0. So let me show you this. So would this be closer to a sine wave or not in harmonic content? This is a square wave with a ton of harmonic content, right? This is another waveform. I've added a 0 here. What does a sine wave look like? A sine wave looks like this, right? Sine wave looks like this, right? There's a huge difference between these two here, right? A huge difference between these two here, right? The closer the two waveforms are together, that's from a physical perspective. You agree that if the waveforms look close to each other, that means probably their harmonic content is similar, right? So now I have something that looks very different at many places here. So I'm trying to get closer to that. So here I add some 0 here and some zeros here, zeros here and zeros here. I'm a bit closer. So you would expect that the harmonic content in this waveform would be less than the harmonic content in the square wave, right? So people went on a little bit further. We will look at the equations for all this, but so they started with this, then added zeros. Then, okay, they realized that this is a nice trick to play with. If I add some zeros here and control my pulse width. If I control my pulse width, they realized, okay, it's interesting. I can get better harmonic content. Fine, I have to raise this value of voltage, right? Because if I want to meet the same RMS value, I will have to, of course, raise this. But they found a nice trick. So people said, okay, how about I do this? Maybe I do, instead of 1 pulse, I do 3 pulses. I do a small one here, a bigger one, and a small one here. And maybe I do this, and I do this, and I do this. Does this look closer to a sine wave or not? Here, instead of rising suddenly, like this is a 0 and then a sudden rise in the value here. Here I have, okay, it's like a sudden bump in the average value of the waveform, and then another bump, but with a bigger duration, right? So it seems it's closer to a sine wave, which rises in value, it rises slowly to a higher value. So here it has a small, this area would have a small average value, this area would have a higher average value, small average value, then 0, right? So you're closer to a sine wave, right? So people used to program this. They call this programmed pulse width modulation. And then they developed better techniques to become, so they found this trick of adding pulses helps. So they realized, okay, how about if I add many, many pulses? So how do I add that to make it as close as possible to a sine wave? So we'll stop here. We'll talk about this next class. So good luck on the exam.